Okay, so this is what, no, y'all left and I realized I hadn't really explained. So removable is if you can plug it. So things like if it's a hole, basically a hole is a removable discontinuity, but things like vertical asymptotes and jump discontinuities, those are not removable because you can't just remove the bad part of the equation and fill it with something else. The only thing that is for us right now are holes. Holes are removable. Because you can remove the bad part of the equation and plug it with something to make it work. Right, so it can't be continuous. Which one are you looking at? 23. It says x equals 0 is a removable discontinuity, but x equals 1 is non-removable, right? Okay, so let me show you. Give me a move. Oh, this thing keeps doing this. You didn't get a good sheet? Okay. Why? Look on the printer. Yeah. Why does he keep doing this? Actually, this thing is down here, isn't it? Get it together. I combined 23 and 24. 23 actually does this. Here, and then here, and then here, and then here. This is 1 and 2. And so it says, find each point of discontinuity. So where are my discontinuities? X equals what? 0 and x equals 1. What type of discontinuity is it x equals 0? A hole. How can you tell it's a hole and nothing else? There's literally a hole in there, right? And the limits are the same as I approach both sides. At x equals 1, what type of discontinuity is that? A jump. And so then it asks me which of these are removable, which ones are non-removable, and give answers. So what is x equals 0? Removable. Because I can plug it. Okay? If I can put one point in there and plug that hole, then I can remove the part. I can remove the part that's making it not continuous and fix it. That's how I remember it. No, because what am I going to plug in here? I would have to plug in a piece of like a vertical line, and I can't do that because then it's not a function anymore, right? So non-removable, removable.
I don't get all points in the not in the domain along with x equals 0, 1.
What does it say? Which are not? Give reasons for your answer.
Find each point of this and then for 23A.
Oh, because they're saying this is a restricted domain, right? It's only through right here, so that you don't have to say that. They're saying the domain for this function is only, what does that go out to? -1 to 2 anyway. So all points in that area are continuous except here and here. It's not a like it doesn't do this. There's no arrows on the end of anything. Because if I were to try to fix that discontinuity, right? If I want, the only way to fix this is to connect them. There's not going to be any way to connect those and it still retain its functionality, because then, right, and so it's a jump. This is filled, this is open. There's no way to make this a continuous function, to draw it without lifting my pencil, without making it no longer a function. You see what I'm saying? So I can't fix it. But this one, I could remove this one point and fill it here, and it's continuous. So I could remove the problem, essentially. Yes, Robert. What value should be assigned to f of 2 to make the extended function continuous at f of 2? What am I referencing? Use the function defined. Here we go. x squared minus 1, 2x, 1, negative 2x plus 4, and 0. This is between negative 1 and 0. This is from 0 to 1. This is when x equals 1. This is between 1 and 2. And this is between 2 and 3. All right, so it says that what value should be assigned to f of 2? F of 2. So I'm looking at between these two, right? Neither one of them have a line under that, so they don't include 2. Does that make sense? So what value would I need to give f of 2 to make the function continuous at 2? So in other words, the left-hand limit and the right-hand limit are going to have to be the same, right? So what did you get? If you look at the graph, it probably makes more sense, yeah. 0.
How?
Okay, so did you look at the graph too? I'll show it to you both ways. How about that? You've got.
I know what a hole looks like on the graph, but I don't know how you tell that this is 5 points.
All right, this is what the graph looks like, right? And then it fills this hole right here somewhere. And there's a little piece over here, but we're not going to worry about that right now. Right now we're talking about right here. What would I need to plug in? What does f of 2 need to be to make that a continuous function? 0.
How do you know that?
Without the graph, if I'm just looking here. Remember what it means to be continuous. To be continuous means that the limit, as I approach that value, has to equal that actual value, right? So from here, this is always going to be 0. So I need to know if I plug in 2 in this equation. So if I plug in 2 here, I'm going to get 0, right? If I plug in 2 here, am I going to get 0? Yes, so I don't even have to do anything else. I'd get 0 both ways, so I need it to be 0. It would be non-removable, right? Then it would be a jump discontinuity, and I couldn't do it. Because it said f of 2, and so this is less than 2, this is greater than 2. It's just there's no line under it. I could technically do that, and now it's a continuous function, right? Does that make sense? 25. Ooh. F of x equals x squared minus 9 over x plus 3, and it says to find a formula for the extended function at the x value given. So what do I need to plug in when x is negative 3? What do I need to make sure y is in order to make that happen? So I think that I will factor because really what I'm looking for is I'm looking for what's the limit as x approaches negative 3 of f of x. And to do that, I'm going to factor cancel out. Well, now I can just plug negative 3 in here. And what do you get? What did they have? They gave they're saying this is the other part of the function what you're left with. Y equals x minus 3. It's still the same thing that we were doing. So like we said, f of x equals this. This is the way I would write this. When x does not equal 3 or negative 3, or negative infinity to negative 3 to infinity, and then negative 6 when x equals 3. You could write it that way, or if you needed a whole equation here, you could put x minus 3 when x equals negative 3. It's the same thing. But it's only for one specific value. Does that make sense? You're still plugging the hole. Yes, either way. Either way is fine. Either way. You're just looking at the end of the day to plug the hole. That's all you're doing. So if I manipulate this, because this is what I'm looking to find, is the limit when x goes to negative 3. So to do that, I algebraically manipulated, just like I was doing with limits. And so what happened was that x plus 3 canceled out, and it left me with x minus 3. So I could say I could put x minus 3 as my extended function part when x equals negative 3, or I could go, since it's only 1 point, I could go ahead and plug it in and say, well, when x is negative 3, that means y is negative 6, so I could do it like this too. Either way, it's fine. It's getting hot in here. Nobody else is hot? Just me. 19. What's wrong, Sophia? Why are you laughing? 19. Do you now? Can I go over what? Yeah. Let's see. F of x equals, this is 19, by the way. Remember, I'm not going to be here tomorrow. Did I tell you A and B? Find each point of discontinuity. Okay, so how do I test it? Because we didn't really test about this. We didn't really talk about this. How do I test to see if it's a point of discontinuity? Put 2 in there and see if it's the same from both sides. But in this case, it doesn't actually include 2. I know there's going to be some type of discontinuity at 2, right? Do you see that? Because x is never actually 2. So something's going on at 2. I know I can already say at x equals 2, there's some type of discontinuity. Whether it's removable or non-removable, I don't know yet, whatever it is. If it's a jump, it's going to be non-removable. If it's an asymptote, non-removable. If it's a hole, then it's removable, right? All right. So the only way to test that is let's put it in each one and see if we get the same number. What happens if we get the same number? Essentially what we're doing is we're doing the limit as x approaches 2 from the left, and then we're doing the limit as x approaches 2 from the right, and we're seeing, are those equal? Okay, so this one would be 3 minus 2, which is 1. This one would be 2 over 2 plus 1, which is 2. So what does that tell me? And it's not removable, right? Because think about what it means. If the limit coming in from both sides is the same, but it's just that 1 point that there's nothing there, then it's a hole, right? But if the limits are different as you come in from either side, then it's a jump. Does that make sense, coming in from both sides? So this tells me that it's a jump, which is not removable. It also tells me that the limit as x approaches 2 of f of x does not exist because the left and the right are not the same. Y'all good? What else? It's been a long day. Yes, Joyce, yes. Yes, 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 yes. Y'all good? All right. There is one little thing I need to tell you about continuous functions before I tell you about IVT. Why? What's wrong? This is an easy lesson today. If a function is continuous, then every operation on that, well, addition, subtraction, multiplication, division, not division, because you can't divide by, okay, so addition, subtraction, multiplication, you could do division as long as no 0 on the bottom. And composition all result in also continuous functions. In other words, if you add one continuous function to another continuous function, you get a continuous function. I lost you? Oh, okay. I thought y'all didn't have any more questions. Y'all got more questions? All right. So here's what I mean by that. Let's say, is that continuous? Yes. We'll just do an easy. Is that continuous? Yes, right? I mean, that's just a basic quadratic and a linear. I can, because they're both continuous, and I established that to start with. Continuous, continuous. I can add, I can subtract, I can multiply, I can do f of x times g of x. And that would, whatever result I get is a continuous function. As long as they're both defined to be continuous to start with, then I can assume the continuity after. So why is this important? Well, this is important because really, this is the one that's going to be the most helpful to you. Do y'all remember composition like that? Okay. Where we plug one function into another. So let me show you just an example that's in your book here. Show that that is continuous, and you don't, without any type of calculator or anything like that, just show that that's continuous. Well, the point here is that I could look at this as saying, okay, well, let's say that, I don't know why my hand keeps doing that. Let's let f of x be x sine x over x squared plus 2. Okay? I know that that's a continuous function, right? The only problem that I might have might come in the denominator being equal to 0. But could that ever equal 0? Why? I'm just saying, just wait, I'm going to show you what I'm doing. Right, because you're squaring a number, even if it's, but the only way that could happen is if x squared was -2, and you're never going to get a negative by squaring a number, right? Are y'all okay there? So this is a continuous function, and I know that, right? What if I said that g of x is the absolute value of x? Is that a continuous function? Yes. Then by this actually a theorem, it doesn't really have a name or anything, but by the properties of continuous functions, then I can say, oh, that scared me. Great, I didn't know what it was. I could say that g of f of x, right, that's taking f of x and plugging it into g, which then looks like my original function, yes? I can say that g of f of x is continuous, even if I didn't know what the absolute value was doing to that function or anything else, because what's inside is continuous and that outside operation is continuous, then that's a continuous function. Y'all okay there before we get to the good stuff? All right, when I give you this theorem, and this is a huge theorem, this is one that highlight in your notebook or whatever, because it's going to, and most of the theorems in calculus make logical sense. It's the applying part of it that gets kind of difficult. This is called the intermediate value theorem. What they will probably test you on most of the time is your understanding of the definition itself, which means there are some things that have to happen in order for this definition to hold true. I have seen them before give you problems where they don't meet every single criteria, and you have to say, well, I can't conclude because. So just know that all of that is part of it. So here's what has to happen. If f of x, which is in just some function, okay, it has to be continuous on some interval AB. Okay, I like a picture. I like to see what's going on. So I might come over here to the side. I've got some function. I'll call this A. I'll call this B. It doesn't even matter what it's doing inside. All I have to know right now is that whatever's happening, it is continuous on this interval. If f of x is continuous on AB, and if C is between A and B. I should probably say it like this. So I'm just going to place some random value C in here somewhere. Then what the intermediate value theorem? Intermediate, kind of like the middle, right? Isn't that what you think whenever you think about intermediate? Is middle? If you don't, then do. Okay. So in the middle, so what this says is I've got this continuous function between these two values. If it's continuous, so it connects between those two, and you've got some x value in between those two, somewhere on that interval on AB, so it's the easiest way. Somewhere on that interval f of c exists. In other words, somewhere on here, there's no way that you can connect this and be continuous where there's not a value that for c on there. This would be f of c, right? There's no way, I can't skip over c no matter what I do. It's going to have a value on there. That's what it means to be continuous. If I don't, then it's not going to be continuous anymore, right? Maybe I jump, but not continuous anymore. If I connect those two endpoints, every point in between has to be defined on the graph somewhere. Does that make sense? That's essentially what it's saying. Okay. The intermediate value thing, like that will be your reasoning. Sometimes you'll get, and we're going to practice with it, some will start out easy, but this is the intermediate value theorem. So you might have a part of an FRQ that says, how do I know that blah is a point on the curve, or that blah exists here? And it's by the intermediate value theorem, because I'm on a closed interval and the function's continuous, I can conclude that there's a value here, kind of thing. All right, let's do a couple examples. Let's see. Not a whole lot of practice with this yet. This is not with intermediate value theorem just yet, but this is with continuity. This all goes together. Find a value of a that makes the function continuous. I have seen this one on multiple choice many times. Find the value of a that makes the function continuous. Any of them? So if I put a 2 in for a, it'll make it continuous. What is it, Craig? It's what? That's exactly right. That's exactly right. What does it mean to be continuous? Tell me the definition of continuity. Okay, the calculus definition of continuity. Okay, that's intermediate value theorem. The limits. I'm talking about limits. The limit, because remember, look, I want it to be continuous. This is the only place where it may not be continuous. So I need the limit as x approaches 1 from the left to equal the limit as x approaches 1 from the right, and I need that to also equal f of 1. That's what would cause me to be continuous, right? Okay, well, the limit from the left, I'm going to use this equation. 1 squared plus 1 plus a. Do you agree or disagree?
I thought you were talking about the value. I thought you were too.
I am. I need to know what's going to go here
Oh,
to make them equal. This one from the right is going to be 1 cubed. F of 1 is also going to use that equation. I need all of these to equal. Well, these already equal, so I'm okay. How do I make 2 plus a equal 1? What is a point of discontinuity that is not removable here? So y'all say 2 is not removable.
Oh,
Not removable. What does that mean, not removable? That's a 3 at the end. Why? That's exactly right. All right, so listen. Removable. I removed the problem, right? Take one of these and this one. It removed from the bottom. Removable. Removable. It's a 3.
well, I thought it was.
No, Robert, what? Robert, no, what are you even talking about? You always do this. But do you see why that one's non-removable? X equals 3 is non-removable. What's happening at x equals 3? I remove, it's an asymptote. It's a vertical asymptote. This is a vertical asymptote. Remember the difference. If everything cancels, it's a whole. It's non-removable. All right. What was I about to say? It's a whole. And it's left in the bottom. If they don't all cancel and it's left in the top, then it's fine. It's still just a whole. If it's left in the bottom, it's an asymptote. All bottoms equal to 0 are vertical asymptotes. Remember when I'm talking about rational functions, my horizontal asymptotes are happening based on the degree of the top and the bottom. And that's it. Horizontal asymptotes are based on end behavior. They're based on what the ends of the graphs are doing. The limit is x approaches infinity, and the limit is x approaches negative infinity. Okay, I'm going to stop there and let you work for a minute. I'm going to leave you some A-Rock stuff tomorrow, which is just what? Which is what? Slope. What? Both of the assignments will be due by, like, it won't be due tomorrow, it'll be due the next day, both assignments. But you got almost 30 minutes now, and tonight's not much. Oh my gosh. Oh, I had already decided. It wouldn't be 25 through 30 because you already did those. 41 through 44. Oh no, that's not all. 47 through 50. What were the first ones? 41 through 44. 47 through 50, we already did 2 of those, I think. But then I also want you to do 52 and 53. And then, of course, your multiple choice ones. And we already did several of these, too. I can't remember which ones. 56 through 59. But we did, I know, no, just stop at 58 because we did 59. If we did any of them, just give them. You can just give them if we did them. If you don't remember, you can. We did it together in class. That's the one with the A. I tried to put the numbers